The Pacific Northwest is supposed to be a place of rain, of grey skies and cedar, and coffee growing cold by a window. But in late June 2021, cities built for drizzle began baking under 115 degrees, heat pressing down on pavement that was never meant to hold it. Roads buckled and buckled again, power lines sagged, transformers failed, and somewhere in the hills, forests that had waited a century for this kind of day started to smoke. It looked like a single summer gone wrong, one freak week on the calendar. Except it wasn't 1 week, and it wasn't a freak accident. What happened in June 2021 was supposed to be impossible for another 30 years. The dome arrives. To understand June 21st, you have to watch the air. High above the region, a vast ridge of pressure began to swell, a dome of descending air that widened and settled over the coast like a lid lowered onto a pot. That lid does two things. It pushes the air down, and as air is pushed down, it compresses and heats, a few degrees for every 1,000 feet. And it locks the sky shut, so nothing below can rise, no clouds can build, no relief can arrive. Day after day, the lid sat there while the sun poured energy onto a surface that had nowhere to send it. Heat accumulated and recirculated, feeding on itself. What meteorologists didn't see coming was how the jet stream had quietly shifted into a pattern it had never held before. The jet stream. The jet stream is a river of wind, 5 miles up, circling the whole planet. In a normal year, it flows loosely eastward, wandering north and south as it goes. But in the spring of 2021, it began to bend, and then to kink. It folded itself into something called an omega block, a shape like the Greek letter omega, a wall of high pressure pinched between two troughs of low. The bend froze, the river stopped moving, and everything beneath it stopped with it. That block is what welded the lid in place and refused to let it move. For reasons nobody fully mapped out, the pattern simply refused to break. And then the Pacific Ocean did something it only does once every few decades: La Niña's shadow. Far from the Cascades, in the open water of the tropical Pacific, the ocean had flipped into a La Niña. Surface temperatures there ran a degree or two below normal, while the western Pacific ran warm, and that quiet split in the sea surface pulled the whole engine of the atmosphere out of balance. You can picture it as a tilt. Cool water means shrinking air, means lower pressure rising over the Eastern Ocean, and that shift sends a signal arcing thousands of miles north, a ripple through the jet stream that forecasters had learned to trace. Where that ripple landed, high pressure liked to settle and stay. La Niña years had produced heat domes over the western states before. They delivered warm, dry, tilted ridges, and the pattern always loosened within a week or two. Nobody expected the lid to snap shut over a place as temperate as British Columbia and hold there, day after day, refusing to lift. Which brings us to the ingredient no climate model had weighted heavily enough. The soil remembers. That ingredient was underfoot. The Pacific Northwest had come out of 2 dry years, and the spring of 2021 had been brutally parched, so by early June, the soils across much of the region carried only half to 3/4 of their normal moisture. The earth beneath the grass was already cracked and sealed. This matters because water is the region's quiet air conditioner. Healthy soil releases moisture through evaporation, and that hidden cooling soaks up a share of the sun's energy the way sweat cools a body. Every rainless summer, that invisible export blunts the worst of the heat. But a dry field has nothing left to give. With no water to evaporate, the ground stops spending its energy on cooling, and the full weight of the sun's arrival goes, undiluted, into warming the air itself. The sun burned down on land that could not sweat, and the surface began to cook in earnest. The inversion layer. High above the valley floors, something stranger was arranging itself. The sinking air inside the blocked ridge compressed as it descended, and compression warms. So a band of hot air rode high over the region, capping the cooler, damper air below it, like a pane of glass laid over a greenhouse. That is an inversion. temperature rising with altitude instead of falling, and the rule of thumb is that warm air sits above cold. In an inversion, warm air traps what lies beneath, and nothing below it wants to rise through the cap. Heat generated at the surface had nowhere to go but to stay. So the region now wore two lids. Deep above, the ridge held the weather out, and just over the ground, the inversion pinned the warming air down in place, sealing it against the valley floors, where the grass had already gone brittle. The air simply waited, and grew hotter with each passing day. Then the mountains entered the equation. Downslope winds. Picture the Cascades as a long wall of rock, and the air riding over its crest, like water spilling down a mountainside. As that air descends into the valleys, the weight of the atmosphere presses down on it, and compression does what compression always does. It heats. Every 1,000 feet it drops, the air gains roughly 5.5 degrees Fahrenheit, and by the time it reaches the valley floors, it arrives drier and far hotter than when it left the ridge. This is adiabatic warming, a quiet physics that had been working on this region for days. The ridge above kept any cloud or storm from breaking the cycle. The inversion kept the warmed air from escaping upward, and now the mountains themselves were cranking the temperature still higher, blowing a furnace wind across the brittle grass. None of these forces were new, and none alone would have been enough. What made this week different was that they had all lined up in the same place at the same time, and on June 27th, all 5 factors converged at once. Lytton burns. There is a village tucked into the steep valley of British Columbia where 2 rivers meet, a town of about 250 people nested against the mountains. On the 29th of June, its thermometer read 121.3 degrees Fahrenheit, the highest temperature ever recorded in the history of Canada. June there usually brings highs around 77 degrees Fahrenheit, and nowhere in the country had ever passed 113 degrees Fahrenheit, until that week. The next day, the hot, dry wind that had been combing the hillsides found a spark, and the fire that followed did not creep. It ran. Within minutes, the flames swept through nearly all of the village, and the people who lived there had only that small window to gather what they could and flee. Before dusk, most of Lytton was ash, and the record it had set the day before became a memorial no town would choose to hold. While Lytton burned, the heat was quietly killing people in their homes. The invisible deaths across the Pacific Northwest and Western Canada, more than 1,400 people died in that week, and nearly all of them died alone, in apartments without air conditioning. The body loses heat through 2 doors, it radiates warmth from the skin, and it sweats, letting evaporation carry heat away. When the air is this hot and this dry, the first door effectively seals shut, and sweating becomes the only way out, until the body's water runs low and the cooling mechanism begins to fail. The heart works harder to push blood to the skin, the organs cook from within, and the awareness of danger fades as the brain heats up. Many of those who died were simply found later, seated in their own living rooms, no fan running, no window open, the stillness of a 100-degree night settling over them. The coroners kept careful lists of ages and addresses, and when the counts were tallied, a pattern emerged from the paperwork. The victims weren't randomly distributed. The equity gap. Across Seattle, Portland, and Vancouver, the dead came almost entirely from the same handful of neighborhoods. The ages skewed old, the incomes skew low, and the addresses clustered where the pavement soaked up heat all day and gave it back all night, where shade was a rare commodity and air conditioning a cost many couldn't afford. 2 neighborhoods across town from each other could feel 5 or 10 degrees apart on the same afternoon. The difference wasn't the sun, it was everything humans had built there, the streets and lots and rooftops, the missing trees. Heat does not respect borders, but it does respect asphalt. And the very systems built to warn people never activated. The warning that wasn't. Alerts are built for disasters that arrive with a bang. Earthquakes give you seconds, tsunamis give you minutes, and the systems that watch for them are tuned to that speed. But heat creeps. It does not spike. It settles. And by the time a warning could have been useful, the moment had already passed. There was no widespread alert for what was coming, not until the damage was done. The same cities that would evacuate for a flood or a storm sat silent, while the thermometer climbed past records that had stood for decades. A heat emergency is invisible until it is not. There is no shaking ground, no wall of water, nothing to film, nothing to photograph, just air that feels heavier with every hour. And so the warnings that should have gone out never did. While people suffered on land, the ocean was beginning to die. The kelp forests. Out in the Strait of Georgia, the water that afternoon read 70 degrees, a number the kelp had never met in all the centuries it had held that coastline. These forests are built for the cold Pacific, for currents that slide down from Alaska at 50 degrees, and they have no defense against the warmth. The blades began to bleaching from the tip, dissolving into a pale, watery green, then brown, until whole stands folded and drifted away on the tide. Where there had been a cathedral of moving light, a nursery for everything that crawled and swam and hid, there was suddenly open water and a silence that the fish had to swim across to understand. The animals did not evacuate. They had no way to know. The warmth moved faster than any warning system nature had ever built, and it did not give them a season to adjust, just a summer to disappear. The mass die-off. When the tide went out on those June afternoons, it left the shore fully exposed, and the heat did the rest. An estimated 1 billion intertidal creatures, mussels, barnacles, sea stars, cooked alive inside their own shells. They had nowhere to retreat. The rock they clung to was the only home they knew, and it became an oven. The beaches did not look deserted. They looked covered, layered with the bodies of things that should have been hidden beneath the water. And the air carried the smell of it. A sweetness turned wrong, the reek of decay rolling in off every cove along the coast. People who came to walk the shoreline left within minutes. Whole colonies died in a single low-tide cycle, a lifetime's worth of generations erased in hours. For the wave, the current, the endless rhythm that had always ruled this coastline, nothing had changed. The water still came, and the water still went. It just came back to a shore that was silent. The barnacles that once armor-plated the rocks now crumbled to the touch. The mussel beds that stretched for meters collapsed into a gray, empty crust. What remained would not regrow soon, which meant the species that fed on them had nothing left to eat. The predator collapse. The first to feel it were the gulls, circling the same coves, finding their usual hunting ground suddenly bare. The shorebirds that scoured the wet sand for tiny lives found nothing moving beneath the surface. They grew thin, their flocks thinned too, and the ones that left did not always come back. The otters that once floated through the kelp on their backs, cracking shells against their chests, now drifted through empty water. Their prey was gone, and hunger does not negotiate. It simply arrives, patient, and then it begins to hollow things from the inside. The fish that schooled in the shallows, feeding on the intertidal bounty, moved on or starved, and with them went the larger fish that fed on them. So the silence did not stay on the beach. It climbed the food chain, one tooth at a time, one empty belly at a time. This is what a trophic cascade looks like from the outside. You never see the process, only the aftermath, a world where the old abundance has quietly been replaced by absence. But the shore was only one thread in a knot of causes, and the knot had not finished tightening. And then scientists discovered something that changed how they understood the entire event. The attribution study. In the months that followed, a team of researchers set out to answer a single question. Could this heat dome have happened on its own? They loaded global climate models with the record of the past century and let the simulations run again and again, thousands of times, each run a separate universe. In some of those worlds, the greenhouse gases were held fixed at their pre-industrial levels. No coal, no oil, no plumes rising from 100 factories. In others, they let the real emissions climb, the actual trajectory of a warming planet. Then they compared the heat domes that appeared in each. The method is brutally simple and brutally effective. Each simulation is an experiment, and over thousands of experiments, a pattern emerges that statistics cannot ignore. They did not ask whether the heat could occur. They asked how often, and how extreme, and how long. The models spat out their totals, and the researchers checked and rechecked the way you do when a result feels too large to be trusted. But the answer did not soften with a second look. It stayed exactly where the data had put it. The answer was a number no one expected. 150 times more likely. The number was 150. That is how many times more likely that June heatwave becomes because of the 1.2 degrees Celsius the planet has warmed since 1900. In a pre-industrial climate, a veteran statistician told them, an event like Lytton's 49.6 would arrive once every 150,000 years. They called it virtually impossible. The same heat, today, is a 1 in 1,000-year event, and it runs about 2 degrees Celsius hotter than it would have been before the coal-fired boilers ever lit. The study carried no comfort in it, only arithmetic. The climate had quietly moved the odds, and the odds had moved the landscape, which means what happened in 2021 is now the new baseline. The return period. That word, once every 1,000 years, carries a weight it no longer deserves. Statisticians call it the return period, and the period is shrinking. In the world those statisticians were handed, a heatwave like this had odds of 1 in 10,000. Stand in a field and wait, and you might stand forever. Today it returns every 1,000 years. By the time the planet has warmed another degree to the target that most governments still claim to honor, model runs put it at every 5 to 10 years. A 1,000-year event, happening once a decade, becomes just a season we learn to name, and there's a reason those timelines might be optimistic. The feedback loops. The reason is a loop. Heat dries the soil, and dry soil soaks up the sun's energy and releases it as still more heat, so the dome over the northwest had baked its own ceiling. The same loop runs at planetary scale. The Arctic melts. Open water swallows the sun's light instead of bouncing it back. The pole warms faster than the equator, and the jet stream between them grows sluggish and wavy. A wavy jet stream is the kind that parks a ridge over a city and leaves it there for 5 days. Each melt widens the wave. Each wave brings the heat that melts. These are not separate stories. They are one machine, feeding itself. One of those loops is already spinning faster than models predicted. The Arctic amplification. The Arctic is the planet's radiator. It bleeds heat into space, and it is warming 4 times faster than everywhere else, a pace that is quietly dismantling the machinery of our weather. That machinery depends on a steep temperature difference between the cold poles and the warm equator. It is that tension that drives the jet stream, the river of wind that herds storms and holds the air in place. But as the Arctic warms, the poles lose their chill, the gradient relaxes, and the jet stream slows down. A slower jet stream begins to wander, snaking far north and far south, and in those wide, lazy waves, weather gets trapped. A wavy jet stream is a locked door. Air piles up in one place and stays, which is how a heat dome is born, a dome that sits over a city and will not move. And in 2021, the jet stream crossed into a regime scientists hadn't seen in observational records. The Omega Block. What trapped the heat over the Pacific Northwest that summer was an Omega Block, so named because the path of the jet stream loops in the shape of the Greek letter omega, a great central bulge of high pressure wedged between 2 troughs. The block sat there, motionless, for days, and when climatologists compared it to the historical record, they found something unsettling. Its shape and ferocity looked less like anything from modern weather charts and more like patterns preserved in tree rings and ice cores, written centuries ago. Those paleoclimate records are the planet's own ledger. They remember summers that predate every instrument we have, and the Omega Block of 2021 stood beside them as if it had stepped out of a page of deep time. It was a shape seen in the ancient climate, alive and spinning in the present. Which brings us to the question everyone started asking, could it happen again? Summer 2022. The following summer, Europe answered. In July of 2022, London recorded 40 degrees, a temperature the city had never reached in its modern history, across a heatwave that broke dozens of national records. Fires swept France and Spain, towns emptied, and the same shape appeared on the maps, another heat dome, another omega block, sitting over the continent and refusing to move. The mechanism was identical. It was the same slow, wandering jet stream, the same locked air, the same bulge of high pressure holding a summer in place. A hemisphere away, the machine was running again, on nearly the same schedule. The records kept falling, and the blocks kept forming, one after another, as if the atmosphere were learning a new rhythm, and then 2023 broke every record 2021 had set. The hottest summer. The year that followed was 2023, and by the time it ended, it had done something no year in recorded history had ever done. Not in the ice cores, not in the tree rings, not in the 2 centuries of direct measurement. The world's oceans ran hot. Day after day, week after week, the surface temperature of the entire ocean sat above every record ever set, sometimes by half a degree. Half a degree spread across the whole Pacific is an almost unimaginable amount of stored heat. And in Antarctica, the sea ice that had always ringed the continent like a wide white belt collapsed. By July, it was missing an area larger than the entire western United States. Scientists who had spent their careers studying that ice admitted, quietly, that they had not seen it coming. It would have been easy to call 2023 an anomaly, a bad roll of the planetary dice. But the records did not snap back. They stayed broken, because something had changed in the Earth's energy balance. The albedo shift. Think of the planet as a surface that decides, every single day, how much of the sun's light it will keep, and how much it will throw back into space. Bright surfaces throw it back. White snow, white ice, pale cloud. Dark surfaces absorb it. Open water, bare rock, wet soil. This is the albedo effect, and it does not stay fixed. As the ice melts, it pulls away like a curtain, and underneath is the dark sea, or the dark ground. That darker ground drinks the sunlight, warms up, and melts the ice that remains, which reveals more dark ground. A loop feeding itself. So the loss of that Antarctic ice was not just a number on a chart. Every missing kilometer of white surface handed a little more of the sun's energy directly to the ocean. The warmth the ice had always reflected away, the ocean started keeping. And in the Pacific Northwest, that warming is playing out in ways no one anticipated. The glaciers retreat. High in the Cascades and across the Olympic Peninsula, the landscape is still dressed in ice that has been there since long before any human drew a map of it. Ancient fields of blue-white glacier, some of them 1,000 feet thick, slow rivers of frozen water that seem as permanent as the mountains themselves. They are not permanent. Over the last century, the glaciers of the American West have lost more than half their volume, and the pace has not been steady. It has been accelerating, decade after decade, until the losses now being measured are arriving years, sometimes decades, ahead of what the models projected. Hear that again. The glaciers are not simply shrinking, they are quitting early, running out of schedule. What research teams expected to see by mid-century is happening now, in the lifetime of the people watching it disappear. And that matters because it is not scenery that is being lost. Meltwater from these glaciers flows down the river valleys through 4 summer months that would otherwise run dry. The ice is a savings account the region spends every hot season, which matters because those glaciers feed the rivers that feed the cities. The water crisis. The Columbia River system carries 60% of its annual flow between May and September, almost entirely from snowmelt and ice. When glaciers vanish, that summer pulse collapses. Rivers that once ran cold and steady through August drop to a trickle by July. exactly when farms need water and cities turn on every tap. The Yakima Basin already rations irrigation in drought years. The Snake River has seen summer flows drop 30% since the 1980s. Salmon can't spawn in warm, shallow water. Municipal reservoirs draw down faster than spring runoff can refill them. It's a mismatch of timing. The region's water infrastructure was designed for a climate where winter snow melted slowly through summer. Now the snow comes as rain or melts in March, and by the time heat arrives, the rivers are already falling. And lower rivers mean drier forests. The fire season. Before 2000, wildfire season in the Pacific Northwest ran from late July through September. Now it begins in June, sometimes May. The forests here evolved for wet winters and cool summers, thick with Douglas fir and western hemlock that hold moisture in their needles and bark. But when soil moisture drops and rivers shrink, those same trees become fuel. The 2020 Labor Day fires in Oregon burned 1 million acres in 72 hours, driven by east winds and record dryness. The 2021 bootleg fire created its own weather, generating pyrocumulonimbus clouds tall enough to inject smoke into the stratosphere. Fire season now overlaps with heat waves, and the combination is lethal. Air temperatures above 100 degrees Fahrenheit, relative humidity below 15%, and forests stressed by months of drought. What used to be a regional problem contained by autumn rains now burns until the first snow. And wildfire smoke is doing something unexpected to the climate system. The smoke feedback. Wildfire smoke isn't just ash and haze. It carries black carbon, microscopic soot particles that rise on convection currents into the upper troposphere and lower stratosphere. Up there, above the weather, those particles linger for weeks and absorb incoming sunlight, heating the air around them by several degrees. That heating can reinforce the same high-pressure ridges that caused the heat wave in the first place. It's another feedback loop. Fire creates smoke. Smoke warms the upper atmosphere. The warming strengthens the ridge blocks cooling storms. The 2020 Western fire season injected an estimated 300,000 tons of black carbon aloft, enough to measurably alter atmospheric circulation over the Pacific. Researchers modeling the 2021 heat dome found that smoke aerosols from fires burning across British Columbia and Alberta contributed to the persistence of the blocking pattern. The effect is small compared to the dome itself, but it's non-zero and it compounds. While the smoke altered weather, it was quietly shortening lives. The health toll. When the dome finally released its grip on the coast, the fires it had been feeding were just getting going. That haze settled over the valleys and stayed. For weeks, the air over Seattle and Portland red as brown, and the emergency departments felt it first. Smoke carries fine particles small enough to pass the walls of the lungs and slip into the bloodstream. Each 10 microgram rise in those particles nudges the odds of a heart attack or a breathing crisis a little higher. The clinics logged record numbers of respiratory calls, of people arriving unable to catch their breath, of inhalers running dry. Across British Columbia alone, the coroner counted 486 sudden deaths in those 5 hot days, against a normal 165. In Oregon and Washington, the toll climbed past 190. The victims ranged from 37 to 97. Most died alone, in homes without air conditioning. The numbers tell a quiet story, and their meaning only sharpens once you set the two threats beside each other. Because heat and smoke don't just add, they multiply. The compound disaster. Each stressor founds a different weak point. Heat drives the heart to work harder, pushing blood toward the skin to shed warmth, rationing what reaches the organs. Smoke does the opposite. Its particles inflame the lungs and thicken the blood, so the heart must strain to push it through narrowed vessels. Separately, either one is a burden the body can usually negotiate. Together, they form a loop, each weakening the defenses the other attacks. The heat wears down the same lungs the smoke has already inflamed. The smoke taxes the same heart the heat has already driven past its comfort. Doctors who worked through that summer describe patients arriving with both crises at once: chests tight, skin burning, oxygen dropping. The compounding made each case harder to treat and faster to turn. And the people least able to absorb the strain are the ones the region is about to have more of. And the demographics most at risk are growing. The aging population. The Pacific Northwest got old quietly, the boomers who moved here in the 70s now settling into their 70s and 80s. Oregon's already one of the grayest states in the West, aging faster than its neighbors and faster than the country as a whole. By 2030, more than 1 in 5 residents will be past 65. That matters because heat kills the old first, and not always dramatically. It's often just a slow smothering, a body that can no longer sweat or sense the danger in its own rising temperature. In the 2021 dome, the median age of Portland's victims was in the 70s. Between 2017 and 2019, all of Oregon recorded 12 hypothermia deaths. That 1 week delivered more than that several times over. Whole neighborhoods are aging too, emptying of the young as the houses fill with the retired and the alone. The strain is measured not in a single catastrophe, but in every elderly person with no way to cool a room. And the place they live was built for a different climate. And the region's housing was never built for this. The cooling gap. A Seattle home was designed around one quiet assumption, that summer means cool. That assumption is built into the walls, the windows, the very wiring of the city. Only 44 of every 100 homes here have air conditioning, less than half the national average. For a century that made sense. The maritime air kept July nights down around the 50s and 60s, and no one needed to hold a room at a temperature the outside air already provided. So homes were built to trap warmth against 6 months of rain instead, with windows placed to catch weak winter sun and insulation that seals heat in just as eagerly in July as it does in December. The heat dome broke that bargain. When the air outside reaches 108, the same architecture that kept winter warm turns every room into an oven, and the houses that never needed cooling become the hardest places to survive. Tens of thousands of people, many of them elderly, simply have no way to lower the temperature except an open window and a fan pushing hot air in circles. Which becomes a crisis when everyone turns on AC at once. The grid under strain. Air conditioning never runs by itself. Every unit that switches on draws current through the same grid, and the hotter it gets, the more current the whole region wants. On the worst days, demand climbs toward peaks the Northwest never designed itself to carry. And at exactly the moment demand surges, the system that must answer grows weaker. Thermal power plants need cool air and cool water to shed their own waste heat, and on a 105-degree afternoon, they produce less, some by 10 or 15%. Transmission lines sag and lose power as their metal heats up, leaking electricity away before it ever reaches a home. So the grid is asked to do its hardest work with its weakest muscles. Generation drops, lines bleed, and demand keeps climbing hour after hour into the evening. Engineers watch the margin between what the region needs and what it can deliver shrink, and then shrink again. And in 2021, the grid came within hours of collapse. The near miss. On the morning of June 28, 2021, Portland reached 115 degrees, and Portland's utility asked everyone to stop using power. Not just appliances, but everything they could possibly spare during the peak hours of early evening. The message underneath was blunt. Demand now sat nearly on top of what the system could carry. Across the region, it was the same. Utilities issued emergency appeals for conservation while warning residents that rolling blackouts were possible, that the lights could simply stop for 30 minutes or 4 hours in rotating blocks. In some places, they did stop, but the larger grid held. Think about what a blackout would have meant there. No fans, no cooling, no refrigeration for insulin, elevators that would not move, and an entire region sealed inside houses built to hold heat. What was already a deadly heat wave would have become something much larger and much faster, all at once. because air conditioning is only one part of what needs to change. The cooling centers. Cities scramble to open their libraries and community centers as cooling refuges, quiet rooms of respite for anyone with nowhere else to go. People came, slowly at first, then in numbers that surprised the volunteers on shift. But the refuge had gaps. Public transit to get there was thin, the word spread unevenly, and the fear of crowded indoor air kept some of the most vulnerable away entirely. The city offered its protection, and the protection had edges. Yet even that imperfect answer mattered. Every person who stepped into the cool, humming stillness of a public library was proof that a human city could respond to heat as something shared, not something each household faced alone. And some cities are beginning to reimagine urban space itself. The urban forest. Portland and Seattle are planting thousands of trees in their lowest income neighborhoods, block by block, hectare by hectare. A mature canopy can pull street temperatures down by 10 to 20 degrees, a difference you can feel in your skin the moment you step out of the sun. It is green infrastructure in the truest sense, living shade grown on purpose, aimed at the corners of the city that baked hardest. The heat does not respect neighborhood lines, but the relief is being planted where it is needed most. And all of it is a long game. A sapling is mostly promise for years, a thin wand of hope that must survive the very summers it is meant to soften. Though trees take decades to mature, and the heat is arriving now. The reflective roofs. Some cities are taking a different route, mandating cool roofs, bright white and reflective surfaces that throw sunlight back out to space instead of drinking it in. A pale roof can stay tens of degrees cooler than a dark one, and every degree off the roof puts less work on the air conditioner below. It is a quiet, almost invisible revolution, visible only from above, thousands of buildings glinting like small mirrors turned skyward. Half the equation is not generating heat at all, and these roofs refuse the sun's invitation before it ever touches the house. And a cooler roof means a cooler street, a cooler neighborhood, a cooler grid that no longer has to strain against the afternoon peak. Yet even these adaptations can't address the core driver, the emissions curve, because here is the uncomfortable arithmetic of this moment. The Pacific Northwest has signed its commitments, promised to zero out its emissions by mid-century, and those promises are real and they matter. But the carbon monoxide, no, the carbon dioxide, already sitting in the sky, works on its own timetable, and that timetable stretches decades. The CO2 a car released in 1995 is still warming the planet right now, still trapping heat every single day. In 60 years, the atmosphere has climbed from 315 parts per million to 426. Cascade summers have run about 3 degrees Fahrenheit hotter than they did in the 1970s, and that warmth is already committed. Even if every last emission stopped tomorrow, the heat already in the system keeps working, the way a kettle you took off the burner still takes minutes to cool. The planet responds slowly. It has a long memory, and it hasn't finished paying back what we've already spent. So the roof, the cooler street, the relief valve, all of it buys us real things. But it can't buy back time. The atmosphere is a ledger written slowly, in ink, which means some losses are already guaranteed. The glaciers we've lost. Nowhere does that ledger feel heavier than on the peaks. Scientists have counted 35 named glaciers in the Oregon Cascades, the ones that existed when this century began. 10 of them have already stopped moving, no longer glaciers at all, just dead ice holding shape. 8 more are gone by 2050, and 8 more critically endangered if warm summers keep coming. And these aren't theoretical losses. Since 1980, Cascade summers have warmed about half a degree Fahrenheit each decade. On Broken Top, the ice is melting at better than 11% a year. The Olympic Peninsula has already given up half its glacial area since 1900, and its researchers say what's left is committed, undone no matter what we do now. They told us plainly, Even if we were perfect citizens and stopped adding carbon tomorrow, it's a century before the climate even begins to react. The heat for these glaciers is already in the system, already on its way down the mountain, which makes the timing of it almost cruel. These are the ice that feeds the cold water streams of summer, that keeps the rivers running when the rains quit, and those glaciers feed cold water streams that salmon need to spawn. The salmon collapse, and warm water is the quiet killer in those streams. For a salmon, anything above 70 degrees Fahrenheit is lethal, not an inconvenience, a death sentence, if the fish can't escape it. The Clean Water Act draws the line at 68 degrees Fahrenheit for the Columbia. Yet rivers across the region now clear that threshold most summers, and some sit there for weeks on end. In the hot summer of 2015, around 250,000 adult sockeye died in the Columbia and its tributaries before they could spawn. In 2021, video showed fish veering into a cold tributary on the Little White Salmon River, covered in red lesions and white fungus, trying to escape water that had hit 70 degrees Fahrenheit, a marathon runner sprinting from a burning building, except there is no finish line for them. Warm water carries less oxygen and it saps a cold-blooded fish's strength at the exact moment it needs every ounce in reserve. The fish can't choose another route. There's only the one river, and the river gets warmer every year. Some of those fish would be watched by people who have fished these runs for generations, for whom the first return is not an event but an inheritance. For indigenous communities, salmon aren't just wildlife, they're identity. The Treaty Tribes. In 1855, the tribes of the Columbia ceded 11.5 million acres, and in return, the United States promised them something it swore was permanent: the right to fish at all their usual and accustomed places, forever. That promise was written into law, signed and sealed, and for generations it held. What was never written down was what would happen if the water itself changed. The river they gathered at has been dammed in 18 places, its cold depths turned to warm reservoirs, and the salmon that once returned by the millions now come back at less than a fifth of that strength. For the tribes, this is not a conservation debate. It is a broken contract, and the party that broke it is the same one that signed it. They watch the first fishing platforms of the season stand empty, the dip nets idle, the baskets that have waited all year for fish that will not come. The treaties promised fishing rights. Nobody promised the fish would survive. And tribes are now suing to force climate action as a treaty obligation. The legal front. The argument is careful, and it is new. Governments have duties, the lawsuits say, not just to their people, but to the systems their people depend on, the ones written into constitutions and treaties. When those systems fail, the courts are the last place you can still be heard. In Montana, 16 young plaintiffs, some of them members of the Confederated Salish and Kootenai tribes, stood before a judge and pointed to a state constitution that guarantees every person the right to a clean and healthful environment. The state had argued its role was too small to matter. The court disagreed, ruling that Montana's own emissions had to be weighed against the health of its children. The same logic traveled. Treaty obligations, the lawyers argued, are not frozen in 1855. They are living promises, and a promise to protect the right to fish means nothing if the water grows too warm for the fish to live. One by one, courtrooms began to accept the science as fact, and the Pacific Northwest heatwave became evidence in courtrooms around the world. The attribution science. This is what finally changed. For most of human history, a heatwave was weather, just weather, a misfortune that arrived and passed and left no one to answer for it. There was no way to look at a sky and say who made it this hot. Now there is. The science of attribution works by comparing two worlds, this one and the one we might have had without a century of fossil fuels, then asking how much more likely a disaster became in ours. When 27 researchers ran the Pacific Northwest heat dome through those simulations, they concluded the event was a once-in-a-thousand-year anomaly, and that climate change made it at least 150 times more likely, roughly 2 degrees hotter than it ever could have been before. They published that finding within weeks, fast enough for it to matter. Suddenly, a disaster is no longer a mystery, no longer an act of God. It has a name, a number, and a cause, and lawyers and policymakers are reading those numbers out loud. Because for the first time, we can prove which disasters wouldn't have happened without fossil fuels. The liability question. So here is the question this march of numbers finally forces us to ask. When the proof is drawn, when the cause is named, who carries the bill? The companies that sold the fuel, the governments that licensed it, or the family standing in the ash of what used to be their home? Cities have already filed suits. Counties have sued. Some cases name the largest oil and gas producers directly, arguing the industry knew for decades exactly what its product would do and marketed it anyway. The courts are still deciding whether that old knowledge creates a legal duty and whether a heat wave can be weighed the way a jury weighs a defective product. These cases move slowly. They crawl through appeals, and final verdicts can take a decade. But the theory has teeth, because attribution science keeps getting sharper every year, and every hot summer adds another exhibit to the pile. The Pacific Northwest heatwave alone caused an estimated $9 billion in damages. The economic toll. Now count what those 3 days actually cost. Washington's roads buckled and softened in the heat. Power lines sagged and melted. Commuter trains stopped running, and the Lake Oroville Dam, which had not shut down since it opened in 1967, went dark for the first time in its history. The orchards gave first. Cherries split on the branch, bursting in the afternoon sun, while workers stood in the shade with nothing to pick. Then the barges slowed on low rivers, and hydropower fell just as demand peaked. Every broken link in the chain costs money, and the chain has hundreds of links. Then the human ledger. Emergency rooms filled on a single afternoon, and the death count, once the numbers were finally tallied, passed 1,000. Hospital stays, missed work, medications lost when refrigerators went warm, insurance claims that never moved fast enough. Those costs are harder to see, but they are every bit as real as a buckled road, and they compound. And insurance companies are beginning to withdraw from high-risk regions. The insurance retreat. The actuarial math is simple, and it is cruel. When a company expects to pay out more than it takes in across a whole region, it stops writing new policies. That is not a punishment and not a political statement. It is arithmetic, and it does not negotiate. Entire states have watched their biggest insurers walk away, non-renewal letters landing in mailboxes one by one. When insurance leaves, the mortgage goes too, because no lender will back a home it cannot protect. That is how a climate risk quietly becomes a housing crisis. That is how a burned acre becomes a boarded-up neighborhood, and a neighborhood becomes a reason to leave. Premiums are climbing faster than wages in the regions that still have coverage, and some homeowners now spend more each year on the policy than on the roof it protects. Others are simply dropped, coverage not renewed, with one word on a form telling them why. Risk. The companies call it pricing reality. The families reading the letter have another word for it. Which raises the question, who can still afford to live in the Pacific Northwest? The migration pressure. So the quiet movement has begun. Families pack the truck with what matters and point it north, or east, or anywhere the insurance premium still makes sense. In California, entire towns have watched their homeowners' policies climb toward unpayable, and the ones with the means to leave are starting to leave. Portland and Seattle watched their own rents climb as newcomers arrived, drawn by forests and rain and the old joke that everyone has a boat but almost nobody owns air conditioning. In Seattle, only 44% of households even have it. The city that was supposed to be the escape is discovering it was never built for what's coming. And somewhere in that churn is a detail easy to miss. The people leaving fire, heat, and drying wells aren't fleeing to safety. They are relocating to places that will face their own climate crisis a few years later, just with a different name on the maps. And the places people are moving to are facing their own climate crises. The cascade effect. For decades, the Pacific Northwest sold itself as the refuge: mild summers, steady rain, mountains that held snow deep into the year. Climate writers called it one of the most livable corners of a warming continent, and people believed it hard enough to move their whole lives there. Then came June of 2021, when the temperature in Lytton, British Columbia, hit 49.5 degrees, and the town burned to the ground the very next day. Portland touched 46.6. The dome sat overhead and simply refused to move, and the mild refuge became, for a handful of days, one of the hottest places on Earth. Scientists later said that event would have been virtually impossible without a changed climate, and the region has warmed more than a full degree Celsius over the last century. The risk map is being redrawn in real time, and the map is not kind to anyone. Because if the Pacific Northwest isn't safe, where is? The global pattern. Here is the part that tends to get lost in a single summer's headlines. The Pacific Northwest did not suffer alone that year. In the very same weeks, Siberia burned through its worst fire season on record, smoke drifting all the way to the North Pole. The Mediterranean caught fire from Turkey to Greece to Italy, and Canada's west coast sat under temperatures that animal species had never encountered there. Satellites watched 3 continents burn at once, releasing more than 2.5 billion tons of carbon in July and August alone, roughly what India emits in a full year. These weren't separate disasters shared by an unlucky planet. They looked like one event wearing different clothes. When researchers laid the heat maps side by side, they found the extremes weren't random. They were synchronized, moving in lockstep across the northern hemisphere, as if the atmosphere itself were trembling on a schedule. And scientists discovered these events were connected by something invisible. The Rossby waves. These invisible connections are called Rossby waves, vast meanders in the jet stream that circle the globe like slow rivers of air 10 kilometers overhead. They ripple north and south in great sweeping arcs, and when one of those arcs bends sharply enough, it can freeze the weather underneath it in place. A ridge of high pressure parks itself over a region, and the sky simply stops moving. The same wave that lifts a dome of hot air over the Pacific Northwest can, at its next crest, pin a cold trough over Europe, while another bend stalls storms over the Atlantic. That is the teleconnection. One hemisphere's heat spike arrives hand in hand with another's flood or freeze. The atmosphere is not a collection of local weather. It is one connected engine, and the waves are its pistons. Those pistons normally sweep through quickly, pushing weather systems along their tracks in a few days. But the jet stream is running weaker than it used to. It flows slower now, and slower air makes wider, lazier waves, which linger instead of passing. And the jet stream's weakening is making these waves larger and slower. The stuck weather. Larger waves mean longer stagnation. A heat dome that used to sit over one city for 3 days now parks there for 2 weeks, and the sun beats down on the same streets, the same roofs, the same pavement, day after identical day. The air stops mixing, so it just cooks, and every morning starts where the day before left off. The effects compound as the hours drag on. Pavement and buildings absorb heat all day and radiate it back all night, so the city never really cools. Overnight lows climb, and the human body needs that nighttime reprieve. Without it, exhaustion sets in fast. Lights stay on, fans spin, and the grid strains under a load it was never designed to carry. Every extra day a dome holds, the danger multiplies. More power failures, more heat stroke, more crops withering in fields that have gone weeks without rain. A short heat spike is an inconvenience. A parked heat wave is a slow disaster that doesn't end when the sun goes down, which means the next heat wave might last even longer. The 2024 projections. The models that track these waves now project what that longer stagnation will look like. By mid-century, climate simulations show multi-week heat domes settling over the Pacific Northwest, with sustained daytime highs above 110 degrees Fahrenheit and nights that barely dip below 80. Scientists run those numbers through the region's infrastructure, and the results are stark. Power lines sag and fail under the load. Transformers cook themselves. Roads soften and buckle, and air conditioning becomes not a comfort, but a lifeline, one that draws on a grid already at its breaking point. When the power goes, the danger arrives all at once. The projections point to mass evacuations, whole cities emptying in the heat, hospitals overwhelmed by the people who couldn't leave. It is not a speculative curiosity, it is a timeline, and woven through every one of those model runs is the same hard fact. There is a ceiling on what the human body and the systems built by human hands can endure, and there's a temperature beyond which cities can't function. The wet bulb limit. Wet bulb temperature is the reading a thermometer gives when it's wrapped in a wet cloth. It measures what heat plus humidity actually do to a living body. At 95 degrees wet bulb, sweat stops working. Your skin can't shed its own heat into air that's already saturated. Healthy people, sitting motionless in the shade, die within hours. Organs cook from the inside, while the outside stays cool to the touch, which is exactly why it's so quiet. There's no dramatic moment, just a body that slowly tells its heart to stop. So when forecasters watch wet bulb maps, they're not watching weather, they're reading a physiological limit, drawn in degrees, and the Pacific Northwest has come closer to it than almost any region its latitude should allow. During the 2021 heatwave, some areas approached 85 degrees wet bulb. The core mechanism. 10 degrees below the fatal line, and the air there still felt like it had weight. That reading wasn't an accident of one hot afternoon. It was the product of 5 separate forces arriving at once, each one feeding the next. A stubborn La Niña parked the jet stream in a distorted loop called an omega block, and the block sat still for days while the sun baked a landscape already drained of moisture. The dry soil stopped cooling the air above it. Then an inversion layer trapped everything, and downslope winds compressed the heat into the valleys, squeezing it hotter with every mile. All 5 had happened before, but never simultaneously, never wired together into a single cascade. No climate model had run that combination, and climate change quietly raised the odds of each one firing at the same time. The baseline itself had moved. The new normal. What happened in 2021 was supposed to be a 2050 event. The temperatures arrived 30 years early, and with them came the things this story has been circling. An attribution science that finally knows how to count blame, feedbacks that compound, infrastructure built for a milder world, ecosystems that tipped and didn't bounce back. It's tempting to call any of it an anomaly, something to recover from. But the recovery model is wrong. This is the beginning of a regime, a new climate that sits quietly underneath every ordinary forecast. The Pacific Northwest story isn't unique. The same sequence is running everywhere, in different latitudes, with different weather and the same arithmetic. The ceiling on what bodies and cities can endure doesn't move, so the ground under our feet does. The maps will keep rewriting themselves. If you want to keep watching them with us, subscribe, and we'll follow wherever the atmosphere decides to go next.